Hello everyone, in this lecture we're going over 2010 Russia Math Olympiad. So this is kind of an interesting problem with some interesting statements. Let's go over the statement. So triangle ABC has perimeter 4, points X and Y lie on rays AB and AC, as you can see here, point X and Y, such that AX is equal to AY, which is equal to 1. So those distances are equal, so we know that this distance here, AX, is equal to this segment here. So you have an isosceles triangle there. Segments BC and XY, they clearly intersect at this point M, so that I forgot to point it out. So point M here, let's call it M. So that's intersection point. Prove that the perimeter of either triangle ABM or triangle ACM is actually 2. So knowing that the perimeter of triangle ABC is 4, and we need to check for the perimeter of ABM, or let me actually first go ahead and draw this AM here, like that, I guess. Okay, so then it is quite plausible that the it is really ABM which will be 2 here, the perimeter, right? Because ACM would be too large for that purpose. So therefore the statement which is kind of bothering us, this either or case here, it is basically telling you that if angle B is greater than angle C, then it must be that the perimeter of triangle ABM is equal to 2. In the other opposite case, where the angle C is greater than angle B, then it really means that the perimeter of triangle ACM is the one which is actually 2. So let me solve this problem for this particular orientation where angle B is larger than angle C. Therefore, I would like to show that the perimeter of triangle ABM is actually equal to 2. That's the result that I would like to prove. Because we are concerned about the perimeters, the perimeter brings to mind the notation S. So little s is for this triangle ABC, we know the perimeter is 4, therefore 2s is equal to 4, or you can say s is equal to 2. I also know occasions where we can use the notation s. It would be related to portions of the edges between the vertices and the touch points of the in-center or the x-center. In this particular case, I will make use of the x-center because I need to really have this distance 2. So far, I have a distance of equal to 1. That's not really useful for me. So what I will do, I will go ahead and extend this line segment here so that I have my, let me actually go all the way here, and I'll do something similar here. Awesome. So I have my X circle. So if that's the point X here, I'm going actually an equal distance beyond X. So AX is 1. I want to go all the way to, let's call the point U here. So I would say U would be somewhere, let's call it here. So U is such that, such that AX is actually equal to AU here. In a similar way, I will go beyond Y to a point V, where, so V would be probably somewhere here. That's point V, such that AY is equal to, oh, sorry for that, so that's a typo. AX is equal to XU, so sorry for that. And similarly, AY would be equal to YV here. Okay, so I constructed U and V in such a way because I know that the perpendiculars from these two, this point and this point here, will actually give me my my x center I sub A. and I know the point I sub A is along the internal angle bisector AI. So okay, so when I draw this circle here, let me do it like this, I guess. So it would be something like this. I would have a tangency here, then another one here, and that's kind of my X center. So let's say that the touch point is right here. Well, it is, well, okay, something like this. So it's probably at this point. Or let me actually fix my X center. It will be easier because, okay, so my X center should be somewhere here, I should say. Okay, there we go. So that's my point I sub A. It's not very convincing. Okay, good. And that point here, let me call it point T. Recall that BM is equal to TC. It's a very well-known result. It's quite easy to prove as well. So I already know BM is equal to TC, where T is the projection of point I sub A onto the line segment BC. Now, so far what we have here is that AU measures 2. So let me write that down. So that's another finding. AU is equal to 2. Notice that that's also equal to AV. But now be observant. So we have BU equals BT because of the tangency here with the X circle. So you can see that. Note that BU is equal to BT, and in a similar way, and CV is equal to CT as well. But then this is kind of like a game changer. So AU, which is simply equal to AB plus BT, I already know is equal to 2. So 2 is equal to AU, which is equal to AB plus BT here. In a similar way, 2 is equal to AV, but AV is the same as AC plus CT. So therefore, I can reduce the problem here, the perimeter of triangle ABM being equal to 2 equivalently. So I claim that the problem reduces to showing that, that's an alternative formulation of our problem. So show that AB plus BM plus MA is equal to 2. Well, 2 is simply AU, right? But now I have this new observation. I can replace AU with AB plus BT. So I'm replacing it with AB plus BT. But then it immediately implies those two are cancelling out. So therefore, equivalently, what I want to show is that BM plus MA is equal to BT here. But wait a second, BT itself can be split into BM plus MT. So that would further cancel things out. So therefore, the problem can be equivalently stated as MA is equal to MT. So that's actually what the problem wants us to compute. So therefore, the problem is asking us to show that this distance here is actually equal to this distance. If I can show MA is equal to MT, then I'm done. Okay, so why would that be? So here at this moment, I will introduce a new technique here. So I will consider the radical axis of two circles. You can say, well, you can only see one circle right now, which is the X circle here. But then I'm also considering the circle centered at point A, which have a radius 0. So I know this is a kind of surprising result for a lot of you here. So notice that the circle centered at point A with radius 0 and this X circle. Now, what is the radical axis of these two circles? Obviously, all I do is I draw the tangencies. So the tangency of the X circle and this circle here is UA and VA. And all I do is I locate the midpoints, which I already know are X and Y by construction. Recall that I constructed U such that x would be the midpoint, or you can say ax is equal to xu, and similarly ay is equal to yv. Therefore, the radical axis of these two circles, namely the x circle here, centered at I sub a, and the circle with center a and radius 0, the radical axis is xy here. But if that's the radical axis, and knowing that m is on that radical axis, it means that the power of point m with respect to those two circles must be equivalent. So therefore, so let me write it down, slide the page slightly here. So we're almost done actually. So I know that the power of point at m with respect to circle centered at I sub a, consider that circle centered at I sub a, the power of that point, the power point m with respect to that x circle is simply mt squared. And how about the power of the same point m with respect to that circle centered at point a with radius 0? It's simply ma squared. But I know that those two entities must be equal to each other because I know m is on the radical axis. So that actually proves that after you take the square root of both sides, mt is in fact equal to ma, but that was exactly what we wanted to show. So if mt is in fact equal to ma, then the perimeter of triangle ABMA would be simply equal to ABBM plus mt, but BM plus MT is simply BT. BT is equal to BU. Therefore, AB plus BU, which is simply AU, is equal to 2, and we're done.